Cholesterol and terpene biosynthesis. And indeed, what we mean by biosynthesis is the way that nature essentially does organic synthesis. How, and particularly, how do you put together carbon-carbon bonds under these mild conditions which you have to have in a biological cell? So I want to start off talking a little bit about cholesterol, and then we'll get into terpenes. Cholesterol, of course, you've all heard about. It's a steroid. This is its structure right here. You can see cholesterol build up in your gallbladder and get gallstones. That wouldn't be a very nice thing to have, but it's just one of the places we look at it. But where's cholesterol supposed to be? Well, of course, it's supposed to be in your cell wall, and it's synthesized in all these cells, and it's an important structural component of the cell wall. And indeed, cholesterol embeds itself in the cell wall. These little things here are supposed to be the cholesterol, with the OH group hanging out into the exterior, greasy part in, the polar part out. And if you don't have cholesterol, your stability of your cell wall is degraded, and so it's an absolutely necessary thing to have. So if you said you want to get rid of cholesterol in your body, well, if you got rid of all of it, you'd be highly dead. So let's not do that. So cholesterol, of course, shows up and does harm as well, and hardening of the arteries, of course, is one of the problems. I had quadruple bypass surgery in 2018, so I know all about this. It's not a good thing. And you also, as I mentioned, cholesterol builds up and gives you one form of gallstones is cholesterol. So cholesterol is necessary, but it's also nasty stuff, and people need to control it. And your body contains about 35 grams of cholesterol. Your diet, you only get about a quarter gram a day, but your body actually makes about a gram per day. And what we're going to talk about actually over today, and today actually Wednesday's lecture is more than today, is how this takes place. And it all comes from this molecule here, which is dimethyl allyl pyrophosphate. We have the diphosphate group on here on this 5-carbon unit, and we're going to see how this works. So this is that same molecule, the dimethyl allyl pyrophosphate, and the first step actually is an isomerization to this, where we just move the double bond over this isopentyl pyrophosphate. And so these two molecules are kind of the key to the whole thing. And remember what this pyrophosphate group is. It's this very large molecule here, which is essentially, if you look at it, about as big as the rest of the molecule. But of course, this renders the whole thing soluble. And again, in terms of chemistry, it's a very good leaving group. So you can think of it as kind of two functions. One is giving solubility to the whole system, but also giving reactivity, because it can very easily leave and make a cation. So anyway, let's look at this. The first step is to isomerize one of these to the other, and of course, which is more stable? Well, you all know this. The internal alkene is more stable, more substituent. So this is actually energetically going uphill. So to power this reaction, so it has to be coupled to something else. So it's an uphill reaction. And how do you suppose you do this in a chemical cell? How would an enzyme do this? Is an enzyme going to apply lots of heat? I don't think so. How about a hydride shift? Well, hydride shifts don't just happen. I mean, hydride shifts happen when you already have a cation. Speaking of cation, well, we could add a proton and then remove a proton. That might work, because when you make a cation, well, then you could do a hydride shift. You could remove a proton, but that would require a strong base. That's not quite so likely. So I'm going to bet on C, because indeed nature has protons around. So indeed, adding a proton is the way it works. It's simple. You add a proton, and then you lose a proton, and that is simply the way the isomerization takes place. So you can imagine that being pretty easy. One enzyme provides a proton, where another enzyme, part of the enzyme, is taking the other proton away. So first step, we ionize. We're going to ionize now the OPP and make a cation from one of them. Which cation is most stable? Well, the cation which is more stable, again, of course, is the conjugated cation. So this first one is more stable, and so we're going now to use this in chemistry. So we did this isomerization. We're going to take another molecule, ionize it, and then the first isomerization is going to attack that cation. and it's going to form a carbon-carbon bond, and it forms a new cation. Now this cation simply loses a proton, and we form this new molecule, which is called geranyl pyrophosphate, which if you look at it is basically the same as what we started with, except we've added this extra unit on here. So as we have now 2 of these 5 carbon units. And these 5 carbon units are basically what we're going to call isoprene units. Isoprene is methyl butadiene, and essentially this, you can think of this as a dimer of isoprene. This is the basis for us for the cholesterol structure. It's going to be the basis for all the terpene structures as well. So this is geranyl pyrophosphate. The word geranyl, that's the same root as the word for geranium, because as we're going to see is that geranium puts off terpenes, and one of the terpenes is geranyl, which is what's one of the odors of the geranium plant. So anyway, here we're just going to show though that what can happen is that this thing can react again, and essentially do a displacement, and it forms this now 3-unit molecule, which again we just lose a proton, and this is called farnesyl pyrophosphate, and this is now a 15 carbon unit. We start off a 5 carbon unit, we went to a 10, now going to a 15, and these 15 carbon species are responsible for making 15 carbon terpenes, which are called sesquiterpenes. And so it's also an important unit. And it turns out the farnesyl pyrophosphate will be the unit we're going to use on Wednesday to make a steroid. But anyway, let's go back to the geranyl pyrophosphate system first. Well, turns out that there's an isomer of geranyl pyrophosphate, which is called narrow pyrophosphate, which leads to a lot of molecules. And the only difference is isomerization around a double bond. So how would you, again, in an enzyme, how would you suppose an enzyme would isomerize a double bond? Of course, the problem is that you can't rotate around a double bond. What can you rotate around? Well, you can rotate around single bonds. So how could we get to a species with a single bond? What do you suppose? There's an intermediate which allows this rotation. And this intermediate is called lineal pyrophosphate. What do you suppose the structure of the intermediate is? Well, think of this. It's an isomer, okay? And it allows rotation around this bond. Well, obviously what we want there is a single bond. So if you look at down here, my choices, what have I got? Well, that's got a double bond. That's got a single bond, all right, but it's all the weird things have happened. We moved this over here. That doesn't make much sense. This one, well, that's still got the double bond. That doesn't work. But look at this guy. All we've done is move the OPP from this carbon to that one. And remember, this could be an allylic system. So that looks like a really good bet. So indeed, B is the structure of lineal pyrophosphate. So how does that work? Well, I mean, I'm just redrawing this in a different conformation. And you lose the pyrophosphate group, and you go to this allyl cation. Now, this allyl cation, of course, is completely delocalized. And I drew this particular resonance structure because I want to indicate what can happen is the OPP can simply come back to the other carbon. As it tells the other carbon, we've gone to this, which is the lineal pyrophosphate. And this can, of course, now rotate, okay? And then it can go back. We lose that again, and we go to this cation, which then, of course, can just now pick up the pyrophosphate at the other end, and we've gone to the narrow pyrophosphate. So there's actually these 3 molecules. They're all isomeric, and it turns out that all 3 of them can serve as precursors to other molecules. It turns out that the narrow pyrophosphate is a precursor to a whole lot of the terpenes, and we're going to do a lot of work with narrow pyrophosphate derivatives. So this is called the narrow cation. This one up here would be the geranyl cation, and the narrow cation will do other reactions as well, as we'll see in a second. Okay, so geranyl cation, narrow cation. Now here's a natural product, a citral. It's a component of citrus. It's called Z-citral because it turns out there's the other isomer where you flip the stereochemistry of this double bond. So what would be a biosynthetic pathway for making Z-citral? Well, so which would you make this from? Would you make it from the geranyl cation or the neryl cation? And once you've done it, would you oxidize or reduce? Well, this is a pretty trivial problem. I mean, what's the conformation here? This is Z. It's going to come. It has to come from the neryl cation, because that's the one that's going to lead. Is going to give you the Z isomer when you move the double bond there. So it's obviously coming from the neryl cation, and it's an aldehyde. Well, this starts off as a cation. You're going to go to an aldehyde. Obviously, that is not a reduction. It's an oxidation. So we're going to add water to the neryl cation, and then we're going to oxidize it. So if we added water here, moving the double bond over, we'd have an alcohol. Then we oxidize that alcohol. So the real question comes up then is, how in the world do we do that oxidation? What's that oxidation all about? Well, I want to talk a little bit about some of nature's other reagents that it uses, and one really common one are the nicotinamide adenine dinucleotide, which is called NAD, nicotinamide adenine dinucleotide, NAD. And basically, it's an adenine up here with this special pyridine up here. So here's the adenine down here. It's linked by a diphosphate linkage to this weird substituted pyridinium ion up here. Now this pyridinium ion is kind of unique because it's a cation, and it's very susceptible to reduction. And indeed, this can pick up a hydride. We're not going to talk so much about where the hydride comes from, but it can pick up a hydride, and it can form this compound called NADH, where I'm just abbreviating the R group with all this lower stuff. And this NADH is a reversible reaction, because it can pick up a hydride, it can deliver a hydride. So it turns out that this can be used to either oxidize or reduce various molecules. If it's going to reduce, of course, it's going to deliver a hydride. If it's going to do an oxidation, it's going to rip a hydride out of another molecule. It's going to pick up hydrides, and that indeed is what it does. And so you can imagine using this as a way of oxidizing or reducing a carbonyl alcohol to an alcohol, or back and forth. Reduction of the carbonyl to an alcohol, oxidation of the alcohol to the carbonyl. So if you deliver a hydride to the carbon of the carbonyl, and then a proton to the oxygen, you've done the reduction. On the other hand, and that's what's going to be done in this particular case that we're talking about. On the other hand, if you got your alcohol, if you rip a hydride off the carbon and steal the proton, you'll go back to the carbonyl. So this actually works both ways. And hydride abstraction and delivery is what NAD plus and NADH is all about. Now there is another variation of this, which is called NADP plus, which the difference is down here at the bottom where I have X. And NAD, that's just a proton, but on NAD plus they put on yet another phosphate. Our nature puts on another phosphate, and it works the same way. And sometimes the NAD plus is used, sometimes NADP plus is used. It just varies from time to time. And indeed, in this particular example, it's NADP plus, which is used for oxidation. So we're going to do an oxidation, and it's from the neryl cation. So it's NADP plus is the oxidation that we're going to use. So this thing will basically, how does it work again? It's going to extract the hydride from the carbon from the alcohol, and then you lose a proton, and that'll give you the carbonyl. So it's a hydride extraction. Now, citral is known as well. This was Z. This is E. It's another one of these terpenes. Again found in citrus. Thus the name. And of course, you'd go through the exact same mechanism, but you would start not with a neryl cation, but with a geranyl cation. So that would be answer B. Okay, so let's look at this a little bit more. This neryl cation, turns out, is really neat. One of the things the neryl cation can do is cyclize. And this is actually its most common thing. We're going to see a lot of this. So the neryl cation can cyclize and predict the product. Well, you just follow the arrows. This double bond is going to tack up there, so of course we're going to get a positive charge on this bottom carbon. And where is it? Where is it? It must be down here somewhere. We moved the double bond up there, and it was down here. Oh, here it is. There it is. It's C down here. Okay. So you can say, well, what's the difference between C and E? Well, got me. I have no idea what the difference in C and E is. They look like the same. But anyway, C, we'll say it's C. That is the alpha terpinyl cation. That's its name. Now, terpinyl sounds like turpentine. Why? Because, well, turpentine is a mixture of terpenes. So it all kind of goes together. But this alpha terpinyl cation is a precursor for a whole lot of molecules. And the simplest thing you can do is just add water, that cation. Just add water, and what you've made this guy. It's terpenol. Okay, it's a component of turpentine, but it's a simple alcohol, and it's one of the most common terpenes around. And this if you feel, a pine tree will emit all kinds of terpenes, and terpenol basically smells like a pine tree. Okay, look at this huge family. This is the alpha terpinyl cation. Doing various reactions, you can go to any of these molecules. It comes from the geranyl diphosphate. Isomerize it first to the narrow system, do the cyclization, and you go to the alpha terpinyl cation. But then doing further reactions, you can make all the molecules in these circles. These are all terpenes. We already did this one just by adding water, so that was a pretty simple example. Let's try to do a second. Let's do this one down here, the cineol. And what is this? Well, this is forming a ring. It's forming an ether linkage. Can you see how you do that? It's actually pretty simple. How would you make the cineol, which is also called eucalyptol, which comes from a eucalyptus tree, not surprisingly. How would you make this? Well, what do you have to do? Well, you have to form a bond from this oxygen to the carbon up there. You see that? And how would you do that? Well, the oxygen needs to attack that carbon. Well, an oxygen isn't going to just attack a carbon. What does an oxygen want to attack? Well, it wants to attack a cation, of course. So how could we get there? Well, look at these. Well, we want the positive charge up here on this top carbon. We want the positive charge right there. So obviously A is the molecule we want. But how do we get from the alpha terpinyl to intermediate A? Well, of course, we just add a proton. So we add a proton, and we go to A, and then we just simply cyclize. Goes up here. It has to lose a proton. I'm not showing that step, but well, I guess I am showing that step here. You lose a proton, and you go to the eucalyptol. So that's pretty simple. Now, all these mechanisms are not quite that simple. Some of them are actually kind of tricky. But when you go around this circle, you should be able to draw a mechanism for every one of these. Okay, isn't that fun? It's going to give you something